Hey, welcome back. We are in day 4 now, and I'm so excited for today because we finally get to do some integration rules. So we hopefully have a really good understanding about what an integral is. Now we're gonna learn the rules, just like we learned with derivatives of product and power and quotient and chain. We have specific rules as well for these integrals. Yay! Okay, so here we are going to first talk about this constant of integration. So a constant of integration means that I'm going to be able to take a graph and move it up or down, okay? And that's going to be this plus c, this vertical here, shift. And when we take an integral, we are always going to have that constant. So kind of think about if I took the derivative of x squared, I would have 2x. What if I took the derivative of x squared plus 9? I would have 2x. What if I took the derivative of x squared plus 1,000 minus 900? I would have 2x. Okay, so when we take the antiderivative, we can't know what that constant was. So that's the little bit of a tough part. So I know that if I took the antiderivative of a 2x, it's going to go backwards to x squared. But I have to put plus c because I have absolutely no idea what that number could have been that I took the derivative of. That's called the constant of integration. So here's what integration is, some vocabulary, the verbs, anti-differentiation, indefinite integration, the nouns, the antiderivative, the indefinite integral. These are all telling me I need to go take the antiderivative here, okay? Now, we know that when we take the derivative of f of x, we get to f prime. And that f looks exactly the same. This is driving me crazy. I'm going to put it over here. It keeps going crazy. Okay, so when I take the derivative of f, I get to f prime. So it stays little f, and then the derivative of f prime goes to f double prime, and I still see little f, little f, little f. When I take the antiderivative of a little f, I get to a big F, okay? Now, if I took the antiderivative of f prime, then one before it was still a little f, plus the constant of integration, okay? All right, so the first rule we're going to see is called the power rule, just like when we learned the power rule with derivatives. But now we're working backwards. So in derivatives, I would bring this 3 down and multiply, and then subtract 1. So we have to go in reverse order. Instead of multiplying and then subtracting, I have to add and then divide. Okay, so the first thing I'm going to do is say, what's my power? And I'm going to add 1 to it. Then I'm going to divide by whatever that new power is. And we always have to have our constant of integration. So this will be true for every single x to the third, x to the negative second. Everything will work except for x to the negative 1. So think about why that's not going to work. If I add 1 to it, I get 0, and then I divide by 0, and oh no, we can't do that. So that's going to be a separate rule we'll learn about later. But I do know that with any other number up here, I get to use this power rule. And don't forget, rewrite as the power rule, okay? Whenever you can. We have talked about this before, that we can separate through addition and subtraction, but not multiplication or division. No, 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 no. All right, so let's do some. Number 1. So I'm going to look at this since it is a plus and a minus as 3 separate integrals going on here. So for the first one, oh, and coefficients, what do they still get to do? Go along for the ride. Okay, so 2 goes along for the ride. Then I'm going to add 1 to the power and divide by the new power. Then I have a plus. 3 goes along for the ride. I'm going to add 1 to the power and divide by the new power. Minus, if you just have the number there, these are super easy. All you do is tag on the variable at the end. So it'd be minus 1x. And that is the power rule because this was technically x to the 0. And then when you add 1 to it and then divide by the new power, you just have x. But I like to just know, like, oh, what derivative gave me -1? -1x. So if it's just a number, then the antiderivative you add on an x to. Don't forget plus c, because we have no idea if there was another thing there or not. So let's simplify that up. 1/2 x to the 4th plus 3/2 x squared minus x plus c. Okay, so let's look at number 2. Well, the first thing I'm going to do with number 2 is rewrite that. So I'm going to get the coefficient out in front, and I'm going to get the power into exponential form. So now I can rewrite it as the power rule. So the 1/2 is going to go along for the ride. Now I'm going to add 1 to that and divide by that new power. So I'm going to divide by 3/2. And I go ahead when I'm doing this, instead of writing that right there, I find it much easier, go away, to say divided by 3/2 because I'm multiplying by the reciprocal. And I just do that all in one step. Plus c. So those 2's cancel. I have 1/3 x to the 3/2 plus c. All right, so that's the power rule. So the next one we're going to talk about is just our wonderful little e, and I love this, like e to the x, never going to catch me with the derivative. Well, guess what? Never going to catch me with the antiderivative, except for the plus c. Okay, so derivative of e to the x, antiderivative of e to the x, e to the x, plus c. And now we have our trig. Getting triggy with it? Na 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 na. All right, so I remember the derivatives of trig. And you guys already know these. You already have them memorized. They are no big deal. You know derivatives. Got it down. Now we're going to take the antiderivative. So now I'm going to say the derivative of what gives me cosine. Well, the derivative of sine gives me cosine. See, the derivative of sine gives me cosine. So the integral of cosine gives me sine. And that's this part right here. So here, the integral of secant squared, we say the derivative of what gives me secant squared? Well, the derivative of tan gives me secant squared. So the antiderivative of secant squared gives me the tan. And then, oh yeah, don't forget plus c, plus c. Similarly, for all of these bad boys, they are just right here from this. Okay? So you definitely have to have these memorized, just like you had to have those memorized, which you already do. Like, do I? Okay, so these are some other trig rules. We will prove these later. They are not as easy as these up here, but I do want you to get them memorized because the proofs are still a little bit tougher, and so it's faster to just know them. So also go ahead and start if you want to make flashcards or whatever, but get those memorized as well. Okay, so let's do an example. So on number 1, I'm going to rewrite, well, not rewrite even, I'm going to think through with doing those separately. The 1/3 is actually with every single thing because it's out in front. The 2 is only with the cosine, okay? So let's see. This 2/3 is going to come along for the ride. The antiderivative of cosine is sine. Plus, that 1/3 goes along for the ride because it's with this. Antiderivative of e to the x, e to the x. We'll add on the plus c at the very end. We don't need to do it every time. We just need 1. And the antiderivative of 1, that's just a number. So I just add on an x with it, except for that 1/3 went along for the ride. And then I have my plus c. Okay? Okay, on the next one, I am definitely going to, pause. This was actually a 1/3 c, but 1/3 times c is just a new c. It's just some constant that we don't know. So all I need to put when I have a number times a number or a number plus a number all going on at the end there, that all gets lumped together to the plus c. So c is that number at the end. Okay, unpause. 2, I am definitely going to rewrite this. So this is going to be 2 tan x secant x plus 2 tan x dx. Don't ask me why I flip-flopped when I multiplied, but I did. Okay, so we're going to think of it as 2 different things. Oh, I know why, because I was like, oh, I know that really, really good. The derivative of what gives me secant tan? So 2 went along for the ride, and the derivative of secant is secant tan. Plus, here when I have my tan, my 2 goes along for the ride, and that is a negative ln of the absolute value of cosine x. That is the one up here that I want you to have memorized. And then I have my plus c. So feel free to rewrite if that's driving you crazy with like the negative and the 2 and all that, but that's up to you. All right, so the next thing I want to talk to you about is even or odd functions and a little bit about what they do. So if I have an even function and I am looking at a graph, so if you kind of see these even functions, we want to think back to our pre-calculus and algebra 2 days. So even functions are symmetrical about the y-axis. So this one right here is an even function. I can see that it's the exact same on both sides of the y-axis. So this one is not that way because it's shifted over. That's not the y-axis where that line of symmetry is. So this is not even. Odd is called origin symmetry, meaning if I took the graph and I flipped it over the x and I flipped it over the y, it looks exactly the same. Another way is to kind of like flip it over the y equals x, and you'll see that as well. But that is up to you, okay, with the odd. And so odd basically looks the exact same on both sides, except you'll see one of them flipped, okay? And that's how I can see an odd. So this is an odd function. This one is definitely not the same on both sides with one of them flipped, so this is also not odd, okay? Now, another way to check for even or odd. So this said that this was x, that's hard to read. I think it says x cubed plus x. So if I plug a negative in for all of those and I simplify, this becomes a negative x cubed and this becomes a negative x. If all of the signs change, so change, then it is odd. So this one says 1 minus x to the 4th. So now if I plug in a negative x here, that negative to the 4th goes away, and I get the exact same. So when none of the signs change, this is an even. But on this one, you're going to see this one changes, this one doesn't change. So you've got a hodgepodge that is neither. So how do we know, like with sine? Let's look at the sine graph. So the sine graph looks, oh, that was maybe a little too high there. But the sine graph looks something like this. Let's try that again. A little bit better. Okay, but do you see how it's exactly the same, but one side is flipped? So I know that the sine graph is odd. And I love to know that about sine, because if I plug in a negative on the inside of sine, then I know that that's negative sine, because on odd graphs, the signs change, not the sine function, but the sign of the coefficient. And so this is awesome to know, and it's a trig thing that I hope you've already kind of talked about, but if not, here you go. Okay, so look at cosine. So cosine looks something like this, and you see how it's exactly the same on both sides of the y-axis. So I know that my cosine graph is even. So when I'm even and I put in a negative, the sign is just a positive. So these are the ones that you will probably have to use at some point for multiple choice, matching, to the multiple choice when you're like, oh my gosh, my answer's not on there, because they use some trig identities and different things to reduce it. So we definitely want to know those. But another thing that's super cool about an even function is if I go from one value to its opposite, so like this value to this value, on odd, the areas cancel out because you have the same amount on top that you did on bottom. Okay, so when you do this with an odd, they cancel and you get to 0, just like on the sine function. When you have an even and you're going from again, that was like negative a to a, so you're going from some value to its opposite, well, this area just gets doubled. So you could choose just to double the area from 0 to a like that, or you could double it from negative a to 0 if that's what you prefer. So these are really great things for even and odd when we are dealing with integration of the functions. So for instance, this one, cosine we know is even, sine we know is odd, and we're going to opposites. So if cosine is even, I know that I could double from 0 to 2 of cosine x dx. Okay, and then we could do more stuff with it. But here, this is the beauty. If we know sine is odd, 0. Yeah. Okay, so that's one that we really love. But these will come in handy as well. And I've seen multiple choice questions where you have to actually know. You may think this is the answer, but it is that one instead. Okay, so the next one says explain why these are equivalent integrals. Well, what type of function is this? If I plug in a negative to all of the x's, I get exactly the same thing because they're all even powers. And so this is an even function going on. And so when I have an even function, then, and I am going from the opposites, then I can just double. Okay. All right, you made it through day 4. Look at you. Good job.